Hello everyone and welcome to this latest webinar from IHS Markit. My name is Alan Tatara, Event Manager for the IHS Markit Technology Group webinar team, and I want to thank everyone for joining us. Today's webinar is, Can Network Hardware Become as Programmable as Software? With the recent transition of programmable network hardware from switches to SmartNICs, there is potential to witness another transformation to increase diversity and innovation in switching silicon. So today our panel will explore the networking transformation enabled by software and programmable silicon, providing sample use cases and guidance for strategists planning network architectures. Our webinar is co-presented by IHS Markit and our partner Netronome. So before we get started, I want to highlight just a few features available for you on the webinar and also how you can participate and make the most of your experience with us today. So the webinar console that you're looking at is completely customizable, so you can open, close, move, or resize any of the windows that you have open on your screen and arrange the console as you wish. Now, at the bottom of your audience console are a number of application widgets which contain additional features available for you. A few buttons I want to point out. One is the resource list widget, and this is where you're going to find additional material about today's topic, including the downloadable slide deck from today's session, as well as other valuable resources. And all these materials can be accessed and downloaded right from your console, so please make sure you take advantage of those during the webinar. And we do want to make this an interactive session, so we've included a Twitter widget, and you'll notice that at the bottom of your screen as well. And this means you'll be able to tweet directly from the console. And today we are using the hashtag SmartNIC. We will also have a live Q&A session directly after the presentation, so we ask you to submit your questions or comments at any time by using that Q&A box on the left side of your screen. And we will try to get to as many questions as possible. And any questions we cannot get to on the call, our panel will follow up with you directly after the webinar. Now let me introduce our panel. First, leading our discussion is Dr. Cliff Grossner. Cliff is Senior Research Director of the Data Center, Cloud, and SDN segment at IHS Markit. And rounding out our panel, we have Ron Renwick, Senior Director of Product Marketing at Netronome. So welcome to both Cliff and Ron. It's great to have you with us. So now let's get started with our presentation. So Cliff, over to you.
Well, thank you, Alan, and thanks everyone for joining. We have what I think is, I always say this, but I'm always excited by our content. And the title of our webinar actually asks a question: Can network hardware become as programmable as software? And I think many of us, and certainly the presenters here, agree that it definitely can and will. The real question is, what are the points in the network that become programmable, and what are the technologies we need to make this happen? And then, of course, how fast does it happen? And I think those are the real questions that we want to try to provide some color on today. And we're going to do that by, first of all, looking at some of the drivers and some of the requirements and changes that have happened server side that drive high-performance networking requirements for the future. We'll take a look at some of the issues around current networks and how they don't scale, lack the agility that we might find in other areas of compute and storage that are more programmable. And then we'll drop down into a discussion about how we can add programmability to network interface cards. We'll then spend a little bit of time on some customer success stories where we already have some good results on the subject. We'll allow our sponsor to say a few words about their unique approach to bringing programmability to networking. And then we'll wrap it up with a short conclusion and have some time for audience Q&A. So with that, let me start by where I think everything begins when it comes to compute, or everything starts in a data center, and that is with compute. And my main point here is that a server is not a server, even though we use the same word for it. And so if we look at a transformation in the data center compute that started, with servers going multi-tenant, that is first running virtual machines and then software containers, we saw a significant change in server complexity and complexion early on in the 2014-2015 timeframe. And then we saw more diversity come into servers around Intel, launched the next generation of x86 with Haswell, and we saw our first ARM-based servers come to market. So now we had more compute options and diversity. The next thing that changed servers is the transition for disk drives, moving from spinning disks to SSDs, and also even more recently, looking at the rise of coprocessors to support artificial intelligence techniques and machine learning. So all of these have moved to change the complexity of servers, making them much more complex, much more both data intensive and compute intensive, even though we still talk about the same server box now. To move things even further along, we also see Intel, Broadwell, and ARM-based processors make their way into the data center for high-performance compute. And in very recent times, we've seen the rise of Open Compute certified servers, really opening servers to a new world of innovation, but also a world of complexity and agility. Now, that is something that we think and believe and know needs to be paralleled by the network and also other subsystems that are present within the server, starting to provide offloads and additional capabilities around algorithmics to support the CPUs and coprocessors that might be embedded in servers. And the other element is that as we move beyond 2021, we see that we anticipate a launch of 7 nanometer silicon wafers and preparing for 5 nanometer silicon. We also know that there's no 0 nanometer silicon, and so at some point we have to go in a different direction. Now that could be highly parallel compute farms, or it could be adding programmability and algorithmics into other elements of the ecosystem for data center, including the network. And that's part of what we believe is going to be driving the movement towards programmability. Now, another element that we believe is going to be driving the movement towards programmability is the connected devices. And we see that we expect the number of connected devices to increase from about 11 billion at the end of 2013 to around 30 billion at the end of 2020. That's a cumulative average growth rate of over 15%. And one of the things that I would put to everyone here is that this is going to be a lot of IoT data that will be traversing the network long before it hits the data center. And the idea that this data should all be processed in the data center, I believe, is already antiquated. And so what we will see is the concept of algorithmic offloads, whether it's in the switches themselves or in the adapter cards that go in servers, that start to process data in flight, so that it's already somewhat computed when it hits the actual server algorithms. And I think that's going to be a pretty large driver for adding programmability into the network. Another element that's transforming compute and also impacting the network in a very large way, as I said earlier, is the movement to virtualized servers and containerized servers. And just to give you a view of how fast that's going, we can already see that we're at a point where probably as many as 60% of servers deployed are either virtualized or running containers. And you could see the light gray area here is actually the inverse, the number of servers that are neither virtualized nor running containers, and that's expected to decrease to 23%. That means that we'll be hitting a point where near 80% of servers could be running a VM or a container over the next 2 years, and this is results from a survey of respondents in North America. So that, again, will drive the complexity of compute and the nature of algorithms to change, providing more opportunity for innovation and computing data in flight on a massive scale. Now, the how big question for the market has to start from servers. And this is our forecast for the server market. And what we see here is that data center server equipment revenue actually is in a bit of a decline and has been rather flat the last number of years. However, what's important is we see a resurgence in growth in the market starting in CY20 and 21. And a large part of this is based upon our forecast, which is based upon a 10-year history of actual worldwide growth in compute capacity shipped. Also looking at the rate of servers becoming multi-tenant and increases in server compute capacity. In the short term, there's a lack of growth in physical servers because servers are continuing to go multi-tenant, and each server, therefore, is better utilized to meet worldwide compute demand, and the demand for worldwide compute has also been declining as smartphone adoption rates have slowed. Now, as we move beyond 2019, we forecast a return to growth because we expect the worldwide compute demand to increase as IoT traffic starts to ramp, and the effect of multi-tenant servers is diminishing as we start to saturate on the number of servers that will go multi-tenant. And so that's driving our forecast. Now, one very important area for fertile research and innovation is the open compute portion of the market. And you can see here that is the green section of the market. And we forecast that's going to reach 7% of servers shipped by 2021, up from 1% in CY16. So that's another area that's going to drive a lot of opportunity for innovation and programmability in the network. Now, the last area that's pushing hard for programmability in the network is the SDN and NFV market. And specifically, when we think about carrier deployment of NFV, which is the the green bar that you see here on the chart, hitting $15.5 billion in 2020. And with NFV, we see the need for programmability in the network to support chaining of VNFs, and also to do functions like network splitting and provide security between VNFs. And this will also drive the potential for offloads and programmability in the network. So with that, I would like to pass the discussion over to Ron to talk to us a little bit about current networks and why they're not agile.
Thank you, Cliff. I really appreciate that. I appreciate the research you guys have done and the forecasting you've put into looking at where the market is going. Looking at this from perspective of someone who's been around adapters for a long time, network adapters, once upon a time we used to think that doing something as simple as a TCP offload was an amazing improvement on a network adapter. Granted, that was in the gig E phase. But as this market has evolved, and you mentioned multi-tenant and virtualization, software-defined networking especially, we're finding that more and more of a CPU's load or a server's load is coming from networking functionality. And I don't mean just passing packets. I mean processing those packets, doing lookup tables, doing firewall functionality, doing distributed security. And what is occurring is as more and more people are packing more VMs onto their servers, they're also burning more and more cycles for networking. The challenge being that adapters, most adapters, are not able to do processing on the adapter. I mean, a lot of adapters can do things like tunnel NCAP and DCAP and VXLAN and so forth, but they cannot be programmed to do specific tunnel types or offload and accelerate switch functionality, data planes, etc. So as we're moving out of the 2010s now and into the 2020s, we're finding 60% sometimes of CPU cycles are being burned out for networking, and especially in multi-tenant environments. That is a negative situation, especially as you mentioned, as we get into a law of diminishing returns on Moore's law. So the challenges that the industry is facing essentially is how can you free up cycles while putting more things in a software-based functionality. And so what we look at often is how are the giants doing? How are the large thought leaders solving their problems? And I think all of us can say, well, the largest cloud providers out there, Amazon, Microsoft Azure, and Google, they're doing things that they're putting more smarts and more programmability down onto the network adapter. When you look at Amazon, when they purchased Annapurna, so they're using 2 by 25 gig, and just a few years ago we thought everyone was going to 40 gig, but no, the 2 by 25 is a much, much cheaper alternative and still provides a significant bandwidth improvement over 10 gig. They're using their own ASIC. They purchased Annapurna for that. Microsoft has done extensive research, development, and publication on their Azure SmartNIC, where they use a traditional NIC ASIC, and they couple that on the sled with an FPGA for smarts and programmability. It can do crypto, it can do QoS, it can do a lot of functionality on the NIC itself, which saves a lot of CPU cycles. Google has their tensor processing unit. The main thing here is, what do all of these people or all these companies share? And the main thing they share is they've got huge R&D budgets. They've got deep acceleration expertise because they're able to find people that can do things like program FPGAs, hire specific and dedicated teams to do the research and the development. And the non-mega scale operators or hyperscale operators, whatever we're calling them these days, don't have those resources. So most of the market doesn't have access to these off-the-shelf solutions. These custom solutions, and they need off-the-shelf solutions in order to solve their problem. So that's where we're seeing this market change from purpose-built NICs with an ASIC that can do a set number of functions to NICs that provide programmability. And we'll get into a little bit of what that programmability can be it an FPGA, multi-core, etc. So let's talk a little bit about programmable NICs, how they're agile, and how they scale. And for that, I'm going to pass back to Cliff for the moment.
Well, thank you, Ron. And I just wanted to share with everyone our newly minted data center network adapter market roadmap. And as Ron said, the evolution in data center Ethernet network adapters was fueled by the prospect to free up CPU cycles by offloading network and storage protocols to the NIC, as well as adding remote memory access that allows NIC cards to access in-memory data without CPU involvement. And this really been driven by, as I said earlier, the fact that a server is not really the same server that it used to be a number of years ago, with the complexity of algorithms changing, the size of the workloads because of server virtualization and containerization, and also with the move to add specialized co-processors, the complexities and the demands within a server on the network component have changed dramatically. Also, as we move to 2500 gig to meet high-performance networking in the cloud service provider and in the carrier network for NFV, offloads become programmable, and specifically potentially adding algorithmic offloads. Now, algorithmic offloads definitely requires the ability to program what those algorithmic offloads should do. And as I said earlier, IoT traffic ramps, and therefore algorithmic offloads take on a much broader importance as we want to now focus on potentially providing compute for data in flight. Once we get past 2021, I think that Ethernet adapter functionality expands, potentially even to include specialized co-processors and high-speed cross-connects to support deployment of large-scale compute clusters, which will probably have to result as we see the rate at which compute inside a server growth starts to diminish. And with that, I'm going to pass, I actually want to talk to you a little bit about the P4 before I pass it back to Ron. And so the P4, I think, is another very important advancement in the marketplace that will, again, move to make network as programmable software. And the P4 is, for those of you that are not familiar, by nature is a protocol-independent language, and it can be used to support different networking technologies such as algorithmic or packet forwarding offloads, whether they be on different devices. And they can also make network protocol handling very agile. And with P4, the developer indicates the required actions that they want using a predefined instruction set and that are compiled into a table and executed based upon a set of predefined match action rules. Now, many organizations use specialized appliances and networks to perform such tasks, and I believe that with the introduction of the P4 language and more advanced uses of it, we'll see those functions then move to networking elements rather than specialized appliance. The other very important element where P4 will help advance the marketplace is to drive consistency by allowing users to create libraries of code describing packet forward behavior, and then they can be assembled to program various devices, ensuring consistency and interoperability across equipment. So the P4, as I said, can be applied to numerous devices, as you see here, and is supported by over 40 member companies, including switch and Ethernet adapter vendors and silicon manufacturers. So it will have, I believe, a quite broad impact in our industry. And with that, now I'd like to pass it back to Ron to talk to us a bit more about some of the Sandbox and programming concepts as P4 relates to network adapters.
Thanks, Cliff. So P4 has a lot of promise because data plane is programmable data planes or programmable NICs or programmable switches are fantastic concepts. But the challenge comes in when you have to program a data plane for every single different device that you have. So if you have different switches or if you have different NICs in your data center, going back to the mega data centers, everyone tends to have different versions of things as they move forward. Are they purchased from this location or purchased from that location? And if you need to do custom work for every single device that you have, it's just not scalable. So P4, being a scripting language, can enable you to run essentially custom data paths to be for specifically like something like a telemetry application. And you can run that data path on a P4-enabled switch or a P4-enabled NIC, and you don't have the vendor lock-in or the multiple vendor challenges, because if you support P4, you have to support the basic code level. On our adapter, we'll get into a little bit more of how we look at things. When you have a custom kernel, a custom data path within the kernel, that drops onto our adapter with the data path extensions. And so a user can actually program custom data paths that will run on our adapter, or they can run on the switch, or they can run on the kernel. It doesn't really matter. And we came out with P4, our P4 was GA, I don't know, about a year ago now. So we've had this capability for quite some time. There are now switches coming onto the marketplace that support this as well. And the basic concept is write once, use many times. And you don't have to be locked into, okay, I only can use these NICs or I can only use this type of switch. I think everyone is a little weary of vendor lock-in. And moving along with that, the questions that come up often is, when I'm running certain workloads, everyone talks about acceleration and offload these days. And everything is still workload specific. Granted, an x86 CPU can do just about anything, but there are certain workloads that do better. GPUs are a great example. I remember when they were only used for video processing and for video display, and then are now being used as essentially multi-core compute devices, have been for some years. Scientific computing, protein folding, machine learning, fantastic applications for GPU accelerators. FPGA accelerators is similar to the Microsoft example I showed earlier, having either the NIC functionality built into the FPGA, which can be quite expensive, or a NIC chip along with an FPGA, work really, really well for things like distributed security or packet processing. They also work for machine learning, deep learning. And then you get into a group that, obviously is near and dear to my heart, which is network accelerators. Some may go back to, the old terminology of network flow processors, but these are accelerators dedicated towards networking functionality. They work really well on distributed storage. They work great on NFV because you can do pipelining. Distributed security is another interesting thing because you can do things like zero trust firewalls around every single VM and put rules and policies in place with things like connection tracking directly on every single virtual machine. And they do pretty good on packet processing as well. But everything has either a cost or a benefit associated with it. What we've found is that when doing custom development work on acceleration devices, if you've got an FPGA or you've got a MIPS or sometimes an ARM SoC or even an NPU, if you're developing custom features for yourself, if you have an FPGA, you need to write in some type of HDL. If you have that expertise, fantastic. Most people don't. If you're writing C code for a MIPS or an ARM SoC, sometimes you find that it doesn't work quite as well as running on an x86. So there's a lot of expertise there as well. Most network processing units require things like microcode. Most people don't have a ton of experience writing in microcode. So when you have custom features, i.e. something like a tagging or telemetry app or a custom tunneling protocol, on a custom device, you find out that there tends to be unpredictable performance, and unless you have a dedicated team that really understands the process, it takes a long time to do your own development work. That's why a out-of-the-box software experience tends to help people the most, or an abstraction layer like a P4. And the other thing is performance, because anything that can do custom work needs to also perform essentially at bandwidth and not burn those CPU cores. And when you look at a device that is running, kernel-based OVS, Open vSwitch being, the most common data plane out there, or user-based, you need to see essentially upwards of 20 million packets per second to get bandwidth at small packet sizes. Anyone can get large packet sizes through, and when you have VXLAN tunneling, you have more processing occurring. So what you want to compare to is what is the performance that you can get on an adapter that's programmable with offload capability and using just standard network capability. Now, we've done a lot of work. You can look it up on our website. We've actually shown that with a single CPU core, we can actually perform by over 50x over competition. And that literally relates back to my earlier discussion about how CPU cores are being consumed more and more by networking. And unfortunately, that's crowding out essentially virtual machines and crowding out applications. So how does this play out? So when I talk about performance per CPU core, what we really look at when you show this, especially at 256-byte packets and below, with an adapter that's using, let's say, a real-world example of 1,000 wildcard flows, 64K exact match flows, and bursting so you have multiple packets per microflow. If you're using a kernel-based OVS or you're using, a user space or DPDK-based, you're going to get certain levels of performance. With kernel, you're going to get about 5 million packets per second, a little bit more. With a user space, you're going to be seeing on the order of 11 million packets per second. You're going to saturate the link on our adapter, and that's only going to burn you one core. But with kernel and user space, you're going to be seeing in excess of 10 x86 CPU cores being burned solely for processing network packets. Now, we'll get into a little bit of what those packets are and how that tunneling mechanism works in just a moment. But even with VXLAN, you see the same situation occurring. You're burning a lot of CPU cores running network traffic, and it's just not reasonable. I clicked a little bit too fast there. I apologize for that. We've got our first poll question. I'd like to hand it back to Cliff.
Well, thank you, Ron. And now it's time for us to ask the audience their opinion. We would like to know, what is your organization's plan to deploy programmable NICs? Are you looking at them? Have you already deployed them? Do you think you'll deploy them by the end of 2017, 2018, 2019, 2020 or later? You don't know, or you have no plans. So if you could please take 10 seconds and respond. We'll wait to see where the audience is with this question. At the same time, while people are responding, I would like to remind you that we will have a question and answer session at the end of this webinar. And so if anyone does have any questions, please go ahead and submit them. I did see one or two already come in, and that's great. Thank you so far for those questions. And with that, we see actually something that does not surprise me is that many people don't know, the majority of people do not know about programmable NICs. And I think that that's because this market is still very new and people are asking the question and need to better understand what are the benefits from this technology. We still see that a small percent have already deployed, and a little bit more expect to deploy by the end of 2017, and there are plans for 2018 deployment. So that's good news, which is actually very timely because now I have a forecast to show you. With that, we're going to drop into looking at success stories, but as part of that, I want to share with you our forecast for data center Ethernet adapters, and what we do break out here is the programmable adapters. And so we're forecasting adapter equipment to grow 5% in CY17 and accelerate in CY18 to 10% and continue to do so through CY21. Now that's quite a bit more than a server unit shipment acceleration. And the reason that when we look at adapter ports, they do parallel unit shipments. But when we look at revenue growth, it's quite a bit higher for adapters, as there are some significant transitions going on in the adapter market, from basic to offload NICs and from offload NICs to programmable NICs, and also large movement from 1 gig to higher speed ports, with all with higher ASPs. So we see that the complexity of the adapter market is changing significantly. So what this means is the proportion of investment in data center compute, if we look at that as servers and adapters, is shifting with more funds invested in adapters for higher server connectivity and sophisticated CPU offloads. That will, allow more server performance and to be used for, or CPU capability to be used for workloads that are more sophisticated as well, rather than applying server resources for networking packet processing. And also, we'll see the ability to have network elements process data in flight for IoT and NFV. So we project programmable NIC revenue growth of 243% and 119% in calendar year 17 and 18 respectively, with growth in double digits out to CY21. When we get to CY21, we project that 11% of Ethernet adapter ports shipped will be programmable, which is up from a very small fraction today. But with that, let me pass it back to Ron, and he can share some of the current success stories from customers that they have.
All right. So it was clear that a lot of folks are thinking, where do I specifically deploy smart NICs or programmable NICs? And a couple of things, we'll just give a couple of brief examples, but one of our customers is using very basic technology, GRE. It's been around for a long time. It's pretty standard protocol. However, this customer needed to modify GRE to meet their custom needs. And they were essentially doing the termination in their CPU. The performance was lagging. Even on a 10 gig link, they were getting about 2 gigs of throughput. But they had no choice. They had specific requirements. And because they were trying to feed a dense VM deployment, i.e. a bunch of small VMs going to a lot of customers, they were not getting performance that they required. So by deploying on a programmable NIC, they could put their Datapath, and we helped them put their custom GRE directly onto our NIC and offload and accelerate that protocol. So to take it back a little bit, any NIC today is going to be able to do the VXLAN termination. Folks ask that question a lot. If Genève or something like that had come to fruition, then NICs would have supported that as well. And what you get into is when you have a custom environment, how do you support your custom environment without burning too much of your resources in order to do so? Because, again, this was essentially a cloud environment where every single CPU cycle counted, and they were measuring it. So by enabling a custom protocol directly onto the adapter, they were able to get rid of their bottleneck, and they were able to increase the number of customers per server. Another specific example is our friends over at Ericsson and their Cloud SDN. Traditionally, they were using OVS in user space with a standard NIC, and they needed to support 220 VNFs. Now, with a traditional NIC and OVS running across 24 cores, i.e. 2 sockets, 12 cores, they were seeing 16 of those cores being dedicated towards networking traffic, and they needed upwards of 3 racks to support all of their VNFs in this use case. So the question becomes, how do you get more TCO? How do you get more VNFs onto a server? And one way to do that is to free up compute. By freeing up compute, what you can do is put more VNFs on your server. So using Netronome Agilio CX, SmartNICs, and offloading and accelerating OVS directly onto the adapter, they were able to significantly reduce their core usage, going from 16 to 1, and they were able to support 220 VNFs directly on 1 rack. Very dense rack, 20 servers per rack. This is a 40 gig technology. So direct comparison, they get 3x better performance simply by adding in a SmartNIC and offloading OVS. Before I get into how Netronome does things and show you a little bit of specifically of our adapter, I'd like to hand back to Cliff to do another poll question.
Well, thank you, Ron. And once again, we're going to ask the audience to share some of their opinions with us. And the question we have is, at what network bandwidth do you think programmable NICs become necessary? And so we could look at 10 gig Ethernet, 25 gig, 50 gig, 100 gig, or perhaps you don't really know. And once again, while we're giving the audience a few seconds to respond to the question, I'd like to remind everyone that now is a good time to answer any other questions you might have for us, as we will be opening up the floor for questions in about 5 to 7 minutes. So with that, let's see what the audience thinks. And I'm actually a little bit surprised that even at 10 gig, we're seeing such a high percent of people that think that's the right place to start putting programmability into NICs. So that's good news for vendors, as I had imagined the audience would look to higher speeds. It's more strongly, but no surprise that we see over 40% of the audience saying that it would be probably 100 gig before they would see the need for programmability. However, we do see a good desire to introduce programmability pretty much at all speeds. good result. So with that, Ron, I'd like to pass it back to you to share the Netronome-specific approach with us.
All right. That was really good news to see that it's 10 gig is where some people are seeing a need. We do support 10, 25, 40 gig. So how does Netronome do things? Now, one thing to be clear, Netronome provides standard PCIe adapters that meet the power profile that support a 92-core programmable ASIC that we develop ourselves. The main thing here is if you look down at the bottom, the Agilio CX itself has the OVS Datapath within it with our software. It mirrors the Datapath that exists within the kernel. So if you notice that you have something like OpenStack Nova, or you've got an Open Daylight controller using OpenFlow, OVSDB for your rules and your management, those get populated within the kernel in the match tables, the actions, and the tunneling protocols. We mirror that, so we just go up into the kernel. We see what exists, and we bring that down to our adapter. So when a packet comes in, if it hits a table, if there's a match on the match table, then we can immediately process that action and deliver it directly to the virtual machine via SRIOV or VirtIO, etc. So we're not changing the data path. We are literally just driving it down to the adapter itself. So if a packet comes in on a traditional server, it comes in to the networking card. It then is pushed up to the CPU, which has to do a match table lookup, sometimes having to hit memory. So you get a slow process there. With ours, it comes in, the match table is populated, and a packet can go much, much faster. So it's essentially a fast path action. So to give you an idea about programmability, we'll also show you something we do with Virtual Router. So that was the OVS data path. Now when you look at a virtual router, when you looked at the OVS data path, let me bring it back a little bit. You had match action, you had tunneling, and then you had match tables, actions, and tunneling. I always bundle up there. With the same adapter and a different software load, you can do things like least prefix match lookup, and next hop, MPLS label lookup. So because our adapter is multi-core and programmable, what you wind up doing is being able to change the personality of the adapter depending on the requirements, i.e. it's programmable. Now, when we launched our adapter, we supported OVS 2.3. Now we support OVS 2.6. So as these software loads and as these data paths progress, as Virtual Router progresses, we will be adding functionality as well. So I won't use some marketing terms, like future-proofing, because that's always something that's people are a little weary of. But as features are added, you can actually add out-of-the-box software loads to enable you to run new protocols. Another thing you can do on a programmable adapter, when we talked about P4, is we do recognize that P4 is an emerging standard. It's fantastic, but some people want to write in like C code instead. So in our development environment with our Programmer Studio, you can write in C code or in P4. Our compiler can leverage both and then drop your data path directly onto our NIC. It's available at openNFP.org, so the choice is yours. You can write in C, you can write in P4 if you need to do something, especially for an SDN application. Another thing that people are interested in is like a custom VNF Acceleration with Berkeley Packet Filter, which is eBPF. If you want to use something like an eBPF, you can program that onto the adapter as well. So the customer or the VNF vendor code can be written in C, run into the compiler. It is then split for ASM code going to the x86 or ASM code going to the NFP. So the concept here is that whatever application you are running,
Hello everyone and welcome to this latest webinar from IHS Markit. My name is Alan Tatara, Event Manager for the IHS Markit Technology Group webinar team, and I want to thank everyone for joining us. Today's webinar is, can network hardware become as programmable as software? With the recent transition of programmable network hardware from switches to SmartNICs, there is potential to witness another transformation to increase diversity and innovation in switching silicon. So today, our panel will explore the networking transformation enabled by software and programmable silicon, providing sample use cases and guidance for strategists planning network architectures. Our webinar is co-presented by IHS Markit and our partner Netronome. So before we get started, I want to highlight just a few features available for you on the webinar and also how you can participate and make the most of your experience with us today. So the webinar console that you're looking at is completely customizable, so you can open, close, move, or resize any of the windows that you have open on your screen and arrange the console as you wish. Now, at the bottom of your audience console are a number of application widgets which contain additional features available for you. A few buttons I want to point out. One is the resource list widget, and this is where you're going to find additional material about today's topic, including the downloadable slide deck from today's session, as well as other valuable resources. And all these materials can be accessed and downloaded right from your console, so please make sure you take advantage of those during the webinar. And we do want to make this an interactive session, so we've included a Twitter widget, and you'll notice that at the bottom of your screen as well. And this means you'll be able to tweet directly from the console. And today we are using the hashtag SmartNIC. We will also have a live Q&A session directly after the presentation, so we ask you to submit your questions or comments at any time by using